above has asked that is the number of nodes agreeing to the particular validation should be over 51% is a compulsion. Right. So as I've told that this is the basis of what we have read just now. It is a flow of the consensus, right? What you are talking about is actually is about a particular consensus, right? So this can be about a proof of work or a proof of stake, right? Where 51% of our attack happens. So number of nodes agreeing to the particular validation should be over 51%. It's not required. We will be we see how 51% is related to this consensus and how we can and how actually all the nodes save these blocks on their end, right? If you still have that question, if you still have not understood something, you can ask it again. Okay. So yeah. So talking about the proof of work, which is the first consensus mechanism introduced in the blockchain world, in which the computing power is used to verify the transactions and add them to the blockchain. Right? So in this blockchain network, anyone can be a miner. There is no restriction as such. You just need a powerful computer because you have to do computation on your node system. The more computation power your system will have, the more chance of your block to be of your system or the node to produce a block and broadcast it to the network to be added as a main block. Right. So in this consensus, we have starting from the left side, right? We have a transaction. Then the transaction goes to the transaction pool where the miners pick up those transactions. They accumulate those transactions, create a block. After that block is created, now using that block, now they try to solve a puzzle through the proof of work, which when is successful, when it produces a specified result which is acceptable, it is then decided to be that it is solved, and now it can be broadcasted into the network for all the other nodes to be nodes to receive it, verify it, and then store it in their state database. So now the broadcasting happens. The verification is done by each and every node on their own end, and the verification of these transactions is a very fast process. It will take less than a second, right? And after that, which they store it in their own database. Right, so this is basically how a proof of work works. So talking about a bit of its history, Satoshi Nakamoto put out this term in 1990, when he was testing out this technology, right? And it was first introduced in Bitcoin, after which we see Ethereum, which is a very refined or I say a upgraded version of Bitcoin, and it utilizes a much more power, which we'll talk about on how Ethereum became much more popular. Right? And the proof of work is also called as mining, and this is a truly decentralized blockchain network, right? And all the other consensus that we talk about, proof of stake or delegated proof of stake, so we have different kind of consensus, but if we talk about it truly and the most decentralized all of them is going to be proof of work, right? But there are reasons why we have moved from proof of work to other consensus mechanisms. So as we have already talked about proof of work, I'll just quickly go through this one slide. So consensus algorithms involves verifying a transaction through the mining process. This section focuses on discussing the mining process and resource consumption during the mining process, right? So as we have talked about mining is about solving a computational puzzle, right? Which is going to take time. And the better machine you have got, the more power it has, the faster, the more computation it is going to perform per second, right? But this is going to take a lot of energy and time on the miner's end. But creating those transactions takes a lot of energy, but announcing them or broadcasting them to the network is going to be almost zero energy, zero time, and almost zero time of verification on the other nodes. So moving on, these are the challenges, right? So it has these challenges as in the 51% risk, which I think most of you must be aware of. Right? It says that if a particular set of miners, they own a 51% or 51% of the computation power of that network, then they are the ones who can who are the actual owners of the blockchain, and they can then introduce any kind of malicious transaction into the system, right? They can do anything, right? Because they own the 51% of that network, right? The another challenges with time consumption, right? Because they have to solve this puzzle. So the time consumption and the resource consumption are going to be the major drawbacks of this proof of work, because they are going to take a lot of computation and a lot of time, which are directly proportional to each other. Okay, and then the last is not instantaneous transaction, right? Transaction confirmation takes about 10 to 60 minutes, so it is not an instantaneous transaction because it takes some time to mine the transaction and add to the blockchain, thus committing the transaction. So I think I'll jump back to the previous the question that Parv has asked about whether the nodes agree to a particular validation should be over 51% is a compulsion or not, right? If it is required that all the nodes should agree to a particular validation, right? So yes, if I'll say the 51%, if yes, if the 51% of the network is owned by a specific identity which is malicious, right, then this is then the node itself, the network itself becomes malicious. So let's say there is this whole network, right? And just similar to a way that if is the person in a company, if he owns 51% of the shares, he is going to be the the final decision maker in the process. Similarly, in the blockchain network also, the majority, because all the nodes are independent, right? They are independent and they can add blocks on their end indefinite of what the other node is adding to their own state. So I'll just let you know how these blocks are saved by a node, right? So once a block is generated, so let's say I am a miner, I have generated the block, I distribute it into a network which consists of all of you people, right? Now when it goes to each one of you, every one of you is going to validate it on their end and save it to their database. So in case, let's say there is user A, it receives the blocks, it validates it, it finds it validated with no malicious transactions. Now it sees that okay, all the requirements, the parent hash is there, the timestamp is correct, and everything is correct. It is going to add it into its blockchain, into its local state. Then there is going to be a node B which also receives the same transaction, but now that it says that no, I think there is a malicious transaction in it, it can fail it, and it does not add it to its own database, right? So now if you have heard about fork, this is a situation which creates a fork, where there are a different set of blocks added to one node and there is a different set of blocks added to a different node, right? But so in that case, this is how a fork is done, and that's why the confirmation of transaction takes about 10 to 60 minutes for the to be finalized, which is in case of Ethereum, it was 32 blocks. That okay, after 32 blocks, it has been observed that if a fork has arisen after 32 blocks, it is going to be removed or it is resolved by the network, right? Now how is it resolved? So let's say there is a new node which is adding itself to the network, right? Now it is going to connect to a lot of peers, right? It is going to connect to 10, 50, 100, as much peers as we allow it to, and it will fetch the data from from all of these nodes and sync that on his own local database, so that it comes in the same position as how all the nodes are, right? But let's say we have a fork in which there is node A which has transaction 1, 2, 3 in its blockchain, and there is a node B which has the transactions as 5, 6, and 7, right? So they have different transactions in their data, in their state DB. Right? Now these transactions are different. So how is the other node that has joined the network, and now it sees that there are two set of transactions, two set of blockchains, chains, right? Not transaction, but two different set of chains. The first chain is 1, 2, 3. The second chain is of 5, 6, 7. So which one is it going to prefer? Which one will it choose? So it will choose which one has the which is adopted by the maximum number of the nodes in that network, right? So it is in similar that, let's say if you heard a statement about something, there are two statements about something, statement 1, statement 2. You will agree to the one to which the most of the people are agreeing to. So that's why if 51% of the nodes in a network, they have the wrong set of data in their blocks, and they overpower by a 51%, then if the new node is going to join in, it will think that those 51% nodes are in majority and must be right, and it will adopt their blockchain, right? So that's why if 51% of the nodes in the network are malicious, then they control it because they own it. If there is going to be someone new, they are going to join that malicious blockchain and not the other one, that malicious chain of blocks. Okay, moving to a question by Saurav. When it comes to solving a puzzle in POW mechanism, what kind of puzzle are we talking about? So if you have seen that, if you must know about that, once a block is created and it has been mined, you must have seen a block hash, a generated block hash in the Explorer, right? When you click on that block hash, it will open up you the details of that block. What is the block number, what is the nonce, and what are the total number of transactions, and etc. All these details, right? So there are two main important factors of solving these puzzles, right? So how this system is resolved is that once so miner is going to collect as many transactions as possible. After collecting all these transactions, it will create a Merkle root hash of all these transactions into a single root hash, a root Merkle hash, if you say. Okay, all the transactions are joined together into a root Merkle hash. Now, using that root Merkle hash, it uses a nonce of that block. So the nonce is a random number. It can be 1, 2, 200, 500, 5000. It can be any amount of number. Now they have to use a hash function using these two, the root Merkle hash and the nonce, as the input to that function, and generate a new hash which has a particular characters at the start or at the end, or that can be any rule. So for example, what we mostly take example is as that the resulting hash of the root Merkle hash and the nonce should be something like 0x0000. Let's say we need 5 zeros at the start of the resulting hash. Now, as you all know, that the hashing is a random process, right? It's if I hash some text, it is going to generate some value which is of a specified length, and if I change just one letter in that text, it is going to completely change the whole hash, right? So it is impossible to know that if I change a certain thing in that text, what it is going to generate. It's impossible to know, right? So that's why it is computational, right? We have a fixed root Merkle hash which is fixed because we have collected all the transactions, but there is this nonce which we have to randomly select and use it with that root hash and root transaction hash and generate a block hash which has a specified rule. Let's say that 5 0 should come at the start. So this is just an example. This is obviously not the case, right? So it has some other complex rules on which it decides that okay, the generated hash is the right one. Moving on to the next one is proof of stake. This is also a popular consensus mechanism which came after proof of work, right? So it is a consensus mechanism for blockchain networks that uses randomly selected validators to produce and approve blocks rather than miners. So it has a certain number of validators. We don't call them miners. There are a validator and which are also selected, right? The selection process now of these validators can vary based on what kind of a proof of it is, right? A proof of stake is going to have a different selection mechanism. A delegated proof of stake is going to use a different selection mechanism, right? But these validators are selected, right? Now, these validators, how they become a validator is by staking some amount of tokens in the system, right? So these validators, they stake the native network's tokens by locking them into the blockchain. In return, they receive rewards based on their total stake, incentivizing nodes to validate the network based on a return on investment. And if we talk about it, it is a way more greener and a scalable version of proof of work. How does a proof of stake works, right? So I will explain you. I think the one in the slide, I'll just go through it and then explain you what Ethereum uses, what kind of a proof of stake of Ethereum uses, right? So nodes are making the transactions, and the validator is going to collect all these transactions from the pool, create a block out of it. And all these validators, right? Or probably let's talk about the proof of stake of Ethereum. And this is the proof of stake which is actually mostly used by all other blockchains if they are talking about a proof of stake, right? As you can see on the second point of this page, this stake is combined with other factors like coinage or randomized block selection to select the validator, right? In case of Ethereum, it is a randomized block selection, but it also, if it is randomized, there is still some criteria based on the staking that they have done, right? So the explanation that we have provided is about the coinage, which you can read out later. So I'll just explain you the most common proof of stake selection process, right? So in order to become a validator, you need to stake some amount, right? In case of Ethereum, it is a minimum of 32 ETH that one has to add it to the network or stake into the network. So these validators, they are generated. After they're generated, they are staking each of their tokens on their own machines, right? And now they have, if they have raised up to the minimum number of stakes that is required, they have become a validator, right? Now that they have become a validator, they have the right to publish blocks and receive the rewards from it, right? Now the selection of this proof of stake is based on the amount of a staking that one has done on the network. So let's say there are two nodes, node A and node B, right? Node A has staked 100 ETH and node B has staked 50 ETH, right? So now A has staked 100, B has staked 50. So A has staked twice more than what B has done, right? Now it would be unfair to give them the equal opportunity in the system, because the first one is staking much more on the network, right? So what happens is that the selection process is going to be random. These validators are going to be randomly selected to publish a block. So we cannot say that, okay, the next block is going to be published by this validator. But what we can say is that the more amount of stake a validator has, the more number of blocks it is going to generate, right? So if we talk about a length of 100 blocks, or let's say 99 blocks, in that case, the node A, which has 100 ETH, which is twice more stake than the node B, it is going to validate or propose twice more blocks than node B, which is in case of 99 blocks, we will talk that 66 blocks are generated by node A and the another 33 blocks are generated by node B. But who is going to generate when, that is unknown, right? That is why it is randomized. And once that once they publish, there is also another selection, the other validators in the node in the blockchain are going to receive that block first, and they are going to verify it. Once it is verified, then the reward is given out to that validator who generated the block, and this block is then broadcasted into the network to all the other nodes. Right? In case that the verification fails, there is a certain amount of token that will be slashed from the validator's account. Okay, so Mujahid has one question that on the POS consensus, that if we hold 51% of coins in circulating supply, can we control that blockchain? Is this practically possible like in ETH? Yes, that is possible. If you own 51% of the coins, right, that means you are going to be selected more than. But this is also a yes no question. This is a yes and no also in this case, right? The reason for that is it depends on the proof of stake mechanism or the core protocol that has been used, right? In case of Ethereum, I said that there is going to be another set of validators which are going to validate that generated block, right? So if we have got a second generation of validators who are validating the block before processing it forward, providing it to the network, right? So these nodes are validating it. So in that case, it is going to fail, right? The malicious actor, even if it holds 51% of the stake, or if it holds more than that, it is not going to provide malicious transactions into the network. It won't do any kind of a fraudulent activity there, right? But in case that we only have in the protocol that, okay, the more the stake validator is, he can generate those much blocks. And if in the network, if he holds 51% of the nodes, right, 51% of the nodes, not the stake, if he had that 51% of the nodes, then yes, it can actually have control over the system, right? So it is not based on the stake, but based on the number of nodes that are in the system. So are there any rules that a particular entity cannot own more than a particular percentage of coins in the staking pool? So currently there is no such rule as of now. You can have as much stake on the node as much as possible, but this is obviously a race between all these validators, right? So if one increases their own staking, the other is going to do so in a similar way, right? But there is as such no limitation on it. And as you can see, there are and this is a very, very much faster process than proof of work, where we are doing a computation. In this one, a validator is selected. It is just directly going to publish a block without any kind of a puzzle that it has to solve, right? So a block is generally relatively published very fast, right? Within seconds, and even in milliseconds if we have less number of transactions, right? So it is going to save us energy, right? This is a proper validation mechanism, but this is also a bit on the centralized side, right? Because now we have the people who have higher stake in the game. They are the ones which are producing the blocks, and therefore it is not completely decentralized and bit on the side of the centralized, right? And it is highly scalable, right? Moving on, this is a difference between these two blockchains. Between these two consensus mechanisms. You can take a look at each of them, and then we will move on. And the next consensus mechanism is proof of authority. They have studied theoretically that blockchain changing from proof of work to proof of stake, but how to do it in practical way to change the consensus algorithm. Right? So, think of consensus mechanism as a way of doing something, right? So it's just a piece of code which can be replaced by another thing, right? So in case of proof of work, there was a certain function which is going to verify the transaction, verify the block, right? So now that verification has changed, that okay, now we don't require verification, or we may require a verification based on the number of validators in the system, that the majority of them should validate this block, right? So generally, if you have seen the London fork, the one in which the Ethereum was upgraded to the proof of stake, in that fork, we call it a fork because there was a hardcore change in the way the Ethereum network was working, right? So any major change in the network, in the core of the network, or in the transactions of the network, what is the current state of the network, if there are these two kind of changes, then we call it as a fork, hard fork. So changing in the practical way, it's a difficult task because we have to upgrade each and every node in the system. So it is basically that in practically what must have been done is that there would have been validator nodes that have been created, right? They would have staked those 32 ETHs on them. They would have started validating from a certain point, right? And I'm currently don't remembering the that's the beacon chain, right? So they started their own beacon chain in reality, and once that system was stable, they merged the proof of work chain with this beacon chain into a single Ethereum chain using a hard fork. These transactions are going to go in. Now that they have a system of proof of stake, they do not require the miners to happen. And then what they did is they asked everyone to upgrade their systems in a certain amount of time, so that they can move on to the newer Ethereum layer. But the old proof of work blockchain is still running, right? Because from a certain point of time when the proof of stake was, this beacon chain was merged into the POW, there were a few miners and people who refused to do so, moving on to this new mechanism, and therefore they let their old chain run exactly without upgrading to the proof of stake system, right? So even if you, I think it's I don't know if it's called a classic Ethereum chain or there is some other name of that proof of work chain which is still working. That's I have not seen or have done any research on how this must have been done practical, but this is an overview of how most of the systems, either blockchain or any Web2 application, is upgraded. So Pav asked that, is it even mutable in terms of consensus mechanism once it is created? So I am not sure what you are asking here, whether it's what are you talking about, mutable about in terms of consensus mechanism. So if you're talking if consensus mechanism can be changed, yes, it can be changed at any time. Because just a set of rules or functions which have to follow. So just like a Web2 application, I just need to do it, right? And a great thing about a blockchain is that, even if we call it a Web3, but all the components that are creating or are able to make it a Web3 are all Web2, right? So it's just a combination of different Web2 components, such like peer-to-peer network, right? A distributed system, right? So consensus mechanism. So these are all Web2 applications. These are simple, which are there from decades. So all of these in a certain combination have created a Web3 thing, a blockchain. So moving on to the next consensus mechanism, which is proof of authority. So since we are running out of time, I'll quickly go through it, and then we will jump to a very important and an interesting part of Ethereum. Because it's a way of efficiently efficient way of running a blockchain. So in this, by proof of authority, they mean that the nodes which are a part of it, they have to stake their reputation in the system, right? So how do they stake their reputation, and what does this authority means, right? So in case of authority, there is no need for the validators to have a stake in the network, but in this case they are pre-approved by the moderators of that blockchain. So let's say I am a person who is owning the blockchain, right? I have my own validator nodes spawned in the network. Now I have a mechanism in place by which I can, via offline process of rigorously validating those validators which want to be a part of the network. There's an offline process by which they are validated or talked about their trust in the network, and after that, if we found it trustworthy, they are added into the network. Right? So it's a completely centralized version where if I say that Facebook wants to add a validator node of it's in my blockchain network, then okay, I know Facebook, I verified offline, and then okay, the verification would be easy, and I add it into the network, and everyone would know that it's a validator node by Facebook, and since it's trusted by most of the people or by the blockchain system, by the blockchain moderators which are handling that blockchain, that's just how these validators are chosen, and based on a randomly selected validators, then they create the block and publish it, right? So it's just as simple as that, right? So there are some terms and conditions for these nodes to work in a way so that they remain to act as a validator in the future also. If they do not, or if they are not able to apply to these conditions, then their access as the validator can be revoked, right? So the validator maintain their computers in good working order. They should possess trustworthiness, high moral standards, and a clean criminal record which is checked offline, okay, outside the system. Then these identities are formally validated in the network and cross-checked in the public domain, ensuring real identities are confirmed. And these candidates are required to invest money and stake their reputation, fostering a rigorous selection process that minimizes the risks of choosing questionable validators and encourages long-term commitment, right? So now, if in proof of stake there could be a person who is malicious, right? Let's say anyone in the network, let's say China, right? They have a huge amount of money in their banks. They can stake as much as possible, right? So this consensus mechanism removes that. No, not anyone with the money can come and join it as a validator. You must be trustworthy. But now it is not totally decentralized. It is mostly centralized, because now it's chosen what validators are chosen. Just like this, there are other consensus mechanisms like DPoS, which is delegated proof of stake, right? And then we have POET, the proof of elapsed time, then proof of concept, proof of time, proof of space. So there are a lot of consensus mechanisms which you can go and read about online. As asked that how is privacy ensured in proof of authority consensus mechanism, right? So okay, so I'm not sure which kind of a privacy. Either you are talking about the privacy of a validator, or you are talking about a privacy of a transaction that happens, right? In a public blockchain, the privacy of a transaction is always transparent. There is no privacy. Everyone knows what transaction goes in. If it's about a validator, then that's the there is no privacy. Like in case of privacy, you are not told about how much reward is provided to it. Okay, the only information that is public is who or possibly it's it totally depends on the moderators. If we want, we can say that okay, if you trust us, You just trust us, and we are trusting the other. We are adding only the trusted validators into the network. And in case you trust us, we are not going to make it anything public. If you don't trust us, what we can tell you is what is the who owns this validator, right? So that at least you know that, okay, whether you want to trust the system or not. And in general case, if you are going to trust one blockchain, it has to make things public on who is going to do validator, or as such, if because it's a manual process, you are adding it manually, right? So what is the reputation of that validator, who owns it, or something like that. Not the complete private, like it won't be completely every information won't be provided, but a very basic of the information which is required for the trust to establish. These are the consensus mechanism which are a core part of the blockchain network, right? Which defines how these which transactions are going to be added into the network. Like that was just a selection process, right, of what is going to be selected and what is going to be added and how. There is another part to it which is about the state change, right? So if I am going to you have heard about smart contracts, right? So these are a piece of application codes on the Ethereum, right? Now if I am the state of the blockchain can be changed either by transferring us tokens, the cryptocurrency, into another wallet, right, which will update the balance of those two wallets which are involved. And the second way is to invoke a smart contract, right? And invoking a smart contract is can happen, but it is it's handled. How is it that the execution of that smart contract function is handled is through EVM, right? So if you have about Java has its own Java virtual machine, which is called as JVM, right? So it's a virtual machine that actually processes the instructions, right? It takes the inputs, and using the bytecode, going through the bytecode, it does the computation and produces an output to it. So that's what's in just like JVM, that's what's an Ethereum is, Ethereum virtual machine, right? Now we call it the functionality is same. The virtual machine, what a virtual machine does is same. We call it as a Ethereum virtual machine because Ethereum has its own set of opcodes and ways to execute a certain piece of code, right? So it has its own set of database. So that's why own set of codes on which it works. Right? So that's why it's specific for Ethereum, and therefore it is called a Ethereum virtual machine. Right? So it is a program which executes scripts which are used to implement certain operations usually in the Ethereum blockchain or a Ethereum blockchain or a Ethereum compatible blockchains. So if we talk about Polygon, so it's a Ethereum compatible blockchain, right? Even that blockchain also uses a EVM, the Ethereum virtual machine, which is created by the Ethereum. So that's a basic explanation of what a virtual machine does. I'll say you can go online and read more about it about what what our EVM is. So you can go to ethereum.org, and over there you can find about the one more thing about is that now that it features smart contracts, right, which is a specific application code which is written in Solidity, right? So as we said, that EVM is a virtual machine which executes something, right? So it is also responsible for updating the state in the blockchain, right? So if there is a set of there is a set of transactions that happen, okay, so there is an invocation of a smart contract. Now it has certain inputs. That's a transaction is going to invoke a smart contract, ask it to perform certain function which changes the state of that data of the variables or anything in that which is related to the smart contract. In that sense, there is a state A. So let's say I just want to move one element from one array to another. Okay, let's say this. Okay, so we have array A, array B. After going through the EVM, if we say that array A has to go to B, now the state of the array A is changed and the state of the array B is also changed. Right. So EVM is the one which is changing that, right? And it's also a Turing complete machine, right? So if you write any smart contract which is compatible with Ethereum, it is always going to produce some output, right? And it can of course fail in case you provide incorrect information. It has the right to fail. If the correct inputs are provided, it is going to produce some output or produce a